so we have the second derivative test. Previously, we had learned the first derivative test, which if you page back, you can easily find it. The first derivative test was using the first derivative to look at the intervals to see if it was positive or negative slope, basically, to decide if we had a relative max or min at the critical numbers. So we are going to use the second derivative test, as you can see here. We're going to test to find extrema. So both the first and derivative tests are ultimately doing the same thing. We are trying to find extrema, but we could use the first derivative or we could use the second derivative. So let's take a look at the second derivative test. It says, let f be a function such that f prime of c equals 0, critical number, and the second derivative of f exists on an open interval containing c. If f double prime of c is greater than 0, then f has a relative minimum at c comma f of c. And if f double prime of c is less than 0, then it would have a relative max. Okay, so let's summarize this a little bit. I guess I should pay attention to the third case, huh? And if f double prime of c is equal to 0, then the test fails. That is, f may have a relative max at c, it could have a relative min, or potentially neither. If we get to this case where f double prime of c is 0, then we would have to use the first derivative test, which we've done already. Okay? Don't forget, right here, actually right here, I should really say, where it's talking about f double prime of c being greater than 0. Remember, we just talked about what that means. That means it would be concave up. And this part right here, where f double prime of c is less than 0, that would be concave down. And it makes sense that if it's concave up, it would have a relative min. And it also makes sense that if it were, come on, scoot down, if it were concave down, it would have a relative max. Okay? And then if it's neither concave up nor concave down, the second derivative is 0, well, then we can't necessarily decipher anything. We'd have to revert back to the first derivative test. Okay? So, let's take a look at this first example. So, what I'd like you guys to do right now, there's a lot you can do so far. I'd like you to at least first find the first derivative, critical numbers, and second derivative. Okay? Do those things first, and then we'll discuss. Okay? Go ahead, put me on pause. So first derivative, nothing too crazy here. We get that f prime of x is negative 15x to the fourth plus 15x squared. To find our critical numbers, we set that equal to 0, and we get that the critical numbers are 0, 1, and negative 1. Second derivative, we get negative 60x cubed plus 30x. So let's check out the second derivative test. Now, remember, if we're just paging back here, we care about, at our critical numbers, is the second derivative going to be positive or negative? So, let's figure it out. Let's figure out what is f double prime of 0. We want to know what f double prime of 1 is, and f double prime of negative 1. Again, why are we choosing these numbers? Well, these are our three critical numbers, and we want to know if it's positive or negative at these critical numbers. So, plug this into my derivative. Here, I would get 0, so this failed. Here, I would get negative 30. So, the fact that that's negative tells us that it's concave down. And if I plug in negative 1, I get positive 30, which would tell us that it's concave up because it's positive, right? So negative, positive. Okay. So right now we know, just based off of the second derivative test, right now we know that here at 1, we're going to have a relative max, right? Because if it's concave down, we'd have a max. And if it's concave up, we'd have a relative min. So far we know that much. We do want to check out 0. Even though it failed the test, we can use our increasing decreasing chart that we use in the first derivative test, to just check out that one. Okay, so, oops, let me get a chart going here. Remember, this is increasing, decreasing, so that has to do with the first derivative. Actually, it's really important here that I use these guys. Any guesses why? We want to use 1 and -1 so we don't pick numbers that are outside of those values, because we already know that -1 and 1 are maxes and mins. So we want to see between those two, you know, would 0 potentially be a max or min? Okay, so we don't want to be misled. All right, so let's choose -1/2 and 1/2. Those make sense. If I plug those into the first derivative, I get that this is a positive number and this is a positive. Okay, so clearly, since it didn't change from positive to negative or negative to positive, we don't have a max or a min. So let's use our derivative speak. I know everybody's favorite. So for relative max, since f prime of 1 equals 0, we're just showing that 1 is a critical number. I guess I didn't really need the comma. And we're also showing that f double prime of 1 is less than 0. This tells us that it's concave down at 1. At the point 1, 2, where'd the 2 come from? Well, I could go back up top and figure it out, right? F of 1 is 2. F of -1 is -2. That'll be useful in our derivative speak. Is a relative, oops, what does that even spell? I don't even know. Ale is a relative max. Great. For the relative min, since f prime of -1 is equal to 0, again, that's to tell us that it is a critical number, and f double prime of -1 is greater than 0. That's to show us that it is concave up. At the point -1, -2, we would have a relative minimum. Also, if you weren't positive, like, you guys can always graph the original function f of x and look on the graph and see, you know, at these points, does it look like I have a max and min? I mean, you guys know what those are on a graph. Check them out. All right, next example. Let's have you guys try this one on your own. So go ahead and put me on pause. This example was the real deal. Literally put everything we've been working on together. That was so fun. Okay, so first derivative, 4x cubed minus 12x squared. Critical numbers, set it equal to 0. We get 0 and 3. Second derivative, we get 12x squared minus 24x. Second derivative test, that's what this whole video is all about. We find out if the second derivative at the critical numbers are positive or negative, or 0. This one was 0, so it failed, so I had to use my first derivative test. And since it went from decreasing to decreasing, no relative max or min at 0. For 3, however, it was concave up because this was positive. So we know since it's concave up, there would be a minimum, right? Okay, so using my derivative speak, in the orange here I said, since f prime of 3 is equal to 0, and f double prime of 3 is greater than 0, at the point 3 comma -27 is a relative min. That's good derivative speak right there. And then tying it all together, points of inflection. So points of inflection, we have to see where the second derivative would equal 0 or undefined. We get 0 and 2. I use my concavity chart using the second derivative, and I noticed that at 0 and at 2, we changed from being concave up to concave down or down to up. So, derivative speak. Since f double prime of x is greater than 0 on -infinity to 0, and f double prime of x is less than 0 on 0 to 2, at 0, 0 is a point of inflection. Since f double prime of x is less than 0 on 0 to 2, and f double prime of x is greater than 0 on 2 to infinity, at 2, negative 16 is a point of inflection. Excellent. So we talked about the second derivative test. It allows us to determine if we have a max or min through concavity.